This problem is about designing the physical layout of a container terminal so that operations run efficiently over many years. The key decisions include where to place the berth area, container yard blocks, gates, maintenance areas, and the internal transport network. Layout design is hard to reverse after construction. That is why we treat this as a strategic optimization problem where a good initial design can reduce long-term cost and increase throughput under real operational uncertainty. Terminal performance depends heavily on the geometry of the site and the placement of major facilities. If the yard is too far from the berth, internal transport cost rises. If the gate area is poorly connected, truck queues increase and congestion spills into the yard. A good design must keep equipment accessible, keep traffic flow smooth, and leave room for future expansion. In practice, the layout must support changing vessel sizes, shifting service patterns, and evolving automation levels. A central challenge is uncertainty. Vessel arrivals are not perfectly predictable, and peak demand periods can be intense. Container dwell times also vary based on customer behavior, customs processes, and policy decisions. Seasonality and demand fluctuations can shift where the bottleneck occurs, sometimes at the berth, sometimes in the yard, and sometimes at the gate. Research often finds that effective terminals tend toward rectangular configurations, but the best shape depends on the terminal's role. Gateway terminals, which store containers for import and export, typically need more yard capacity, so they tend toward a more square footprint. Transshipment hubs prioritize berth capacity for vessel-to-vessel transfer, so they often favor elongated rectangles along the waterside. The economic impact of layout design is substantial. A well-designed layout can improve operational efficiency by 15 to 30%. It can also reduce equipment investment requirements by 20 to 25%, because better flow and better utilization reduce the need for excess equipment. Because redesign after construction is extremely expensive, good initial decisions have outsized value. We will cover multiple tiers. Tier 1 provides a stochastic programming formulation that captures uncertainty through scenarios. Tier 2 uses branch and bound with intelligent pruning to systematically search assignments. Tier 3 uses a harmony search metaheuristic. Tier 5 introduces an integrated digital twin for system-level simulation. Tier 7 focuses on a human and AI symbiotic partnership for practical decision-making. In Tier 1, we treat the terminal as a set of facility types that must be assigned to candidate locations. The key is that many operational parameters are uncertain, so we use scenarios to represent alternative demand and flow conditions. The objective is to minimize expected cost across scenarios, including transportation costs from flows between facilities and a penalty when utilization exceeds a target threshold. This makes the model sensitive to congestion risk under peaks. We define the set of facility types, which includes elements like berth, yard blocks, gates, and other components. We also define the set of potential locations where these facilities could be placed. Finally, we define a set of scenarios. Each scenario represents a different realization of uncertain parameters, such as flows or area needs, and each scenario has an associated probability. Stochastic parameters capture the uncertain operating environment. Expected flows between facilities vary by scenario, and transportation costs between locations can also be scenario-dependent. We also include area requirements for facilities under each scenario, as well as the probability that each scenario occurs. These parameters allow the model to optimize against a distribution of possible futures rather than a single forecast. The first decision variable indicates whether facility I is assigned to location J. This is the core layout decision. Additional variables represent flows between facilities under each scenario and the utilization level of each facility. These variables connect the physical layout to operational performance and congestion risk. The objective minimizes expected cost across scenarios. It includes transportation costs driven by flows moving between facilities and distances implied by their assigned locations. It also includes a penalty when utilization exceeds a target threshold. The penalty coefficient controls how aggressively the model avoids high utilization designs that are prone to congestion during peaks. This constraint ensures every facility is placed exactly once. Operationally, it enforces a complete layout decision with no missing facilities and no duplicate placements for the same facility. It also sets the foundation for the rest of the model because flows and capacity terms depend on knowing where each facility is located. This constraint prevents spatial overlap by ensuring that the total area assigned to a location does not exceed the area capacity of that location. It can be interpreted as a feasibility check for physical space. In practical terms, it enforces that the site can actually fit the selected combination of facilities and that no single location is overloaded beyond its spatial limits. Flow conservation maintains material balance. The flows defined by the model must match the expected demands under each scenario. This ensures the layout is evaluated using consistent throughput assumptions and that the modeled internal transport flows are physically meaningful. This constraint defines utilization as flow divided by capacity. By explicitly computing utilization, the model can penalize designs that operate too close to capacity. This is important because terminals are vulnerable to nonlinear congestion when utilization becomes high, especially under peak arrivals. This figure summarizes the stochastic layout optimization model. It shows how facility placement decisions connect to flows, costs, and capacity constraints under uncertainty. The visual reinforces that the problem is more than drawing a map. It is about creating a layout that performs well across scenarios rather than being optimal only for a single average day. The example uses a simplified three-facility layout with berth, yard, and gate. It introduces two scenarios, peak and off-peak. The peak scenario has probability 0.3, and the off-peak scenario has probability 0.7. The flow volumes differ by scenario to represent surges and normal conditions. The reported optimal design minimizes expected transportation cost while keeping capacity feasible under both scenarios. The reported expected cost is 1,250 units. The berth is placed waterside, the yard is placed centrally to reduce average internal transport distances, and the gate is placed landside to support truck access and reduce landside congestion. Tier 2 addresses practical instances where exhaustive search would be too slow. Branch and bound explores assignments systematically but uses bounds to eliminate large portions of the search tree. A lower bound estimates the best possible completion of a partial assignment. If that bound is already worse than the best known solution, the node is pruned. Intelligent pruning strategies include feasibility checks, distance-based cost estimation, and symmetry breaking. This figure illustrates the structure of the search tree and how pruning reduces the number of nodes explored. You can interpret it as focusing computation only on promising regions of the assignment space. The main operational value is that we can still obtain optimal solutions for moderate sizes while avoiding the full factorial explosion of naive enumeration. This code defines a solver that stores facilities, location coordinates, flow matrices, cost matrices, area requirements, and location capacities. It includes a distance function and a partial cost function that computes the transportation cost for currently assigned facilities. This is the core cost driver in layout decisions. This portion defines a lower bound calculation. It combines the cost of the current partial assignment with an estimate of the minimum additional cost needed to place remaining facilities. The goal is not to be perfectly tight, but to be informative enough that many unpromising branches can be pruned early. This section defines feasibility checks, such as whether a location is unused and whether the facility's area requirement fits the location capacity. These checks prevent wasting computation on infeasible partial solutions and improve pruning performance. This section implements the main branch and bound loop. It pops nodes from a priority queue, prunes nodes whose bound is worse than the current best, and branches by assigning the next facility to feasible locations. When a full assignment is reached, it updates the best solution if the cost is lower. This is how the algorithm guarantees optimality while avoiding full enumeration. In the reported example with 4 facilities and 6 locations, the algorithm explores 847 nodes. It prunes 73% of search nodes through bounding, and it reports a best total cost of 2,847.5 units. The reported assignment places the berth at location 0 with coordinates 0, 0, which is the waterside position. It places yard block 1 at location 5 with coordinates 5, 5 as a central position, yard block 2 at location 2 with coordinates 10. 0 as an intermediate position, and the gate complex at location 4 with coordinates 0, 5 as a landside position. Tier 3 uses harmony search, a meta-heuristic inspired by musical improvisation. A layout solution is treated as a harmony, meaning an assignment of facilities to locations. New harmonies are created by selecting assignments from a harmony memory, applying small adjustments, or choosing random alternatives. This gives a practical balance between exploiting good layouts and exploring new ones. This figure presents the key components of harmony search, including the harmony memory and the improvisation mechanism. The convergence curve illustrates how solution quality improves over iterations as the algorithm learns better combinations of facility placements. This code defines the harmony search framework and sets key parameters such as harmony memory size, memory considering rate, pitch adjusting rate, and the maximum iteration count. It also outlines helper concepts like distance and evaluation, where evaluation aggregates flow times cost times distance and includes penalties for capacity violations. This section defines feasibility and the generation of random feasible harmonies. Feasibility typically requires unique location assignments and no capacity violations. If a random attempt fails, the method falls back to a sequential approach. This is important because meta-heuristics must maintain feasible solutions to make comparisons meaningful. This portion shows improvisation and optimization. For each facility, the algorithm chooses an assignment from memory with a probability given by the memory considering rate, otherwise it explores randomly. With a probability given by the pitch adjusting rate, it performs a small local change such as swapping two facilities. Over iterations, it keeps better solutions and replaces worse ones. The reported example uses a harmony memory size of 20, a memory considering rate of 0.9, and a pitch adjusting rate of 0.3. The algorithm runs for 1,000 iterations. These settings emphasize using good memory solutions most of the time while still allowing local adjustment and occasional exploration. The reported final cost is 2,798.45 units. This represents a 12.3% improvement over the initial random solution. The reported robustness is that 89% of final solutions are within 5% of the global optimum. The reported assignment snapshot places the berth area at coordinates 16, 0. It places yard block A at coordinates 0, 8, yard block B at coordinates 8, 0, the gate complex at coordinates 8, 8, and maintenance at coordinates 4, 4. Tier 5 introduces the integrated digital twin, which is a virtual replica of the terminal ecosystem. It models berth operations, yard management, gate processes, equipment scheduling, and traffic flows together. The digital twin synchronizes with real operations using sensors and operational databases. It enables what-if analysis for layout modifications and exposes bottlenecks that are not obvious from static models. This figure shows how multiple subsystems are connected: sensing, tracking, simulation, and analytics. The point is to capture interdependencies. For example, berth allocation affects yard selection, which affects gate processing, which affects truck queues. The digital twin treats these as coupled dynamics rather than isolated part. In the Port of Rotterdam example, adding a fourth yard block increases storage capacity by 25%. However, the simulation reveals an internal transport bottleneck that reduces overall throughput by 8%. After redesigning the internal road network, the system achieves a 12% throughput improvement while retaining the expanded storage capacity. The digital twin is reported to achieve 96.7% accuracy in throughput forecasting. It is also reported to enable proactive adjustments that prevent 78% of potential bottlenecks before they impact operations. This highlights the value of continuous validation and operational feedback. Terminal layout decisions combine quantifiable objectives with qualitative judgment. Throughput and cost can be modeled, but safety, regulatory compliance, flexibility, and community impact require human context. The Centaur model combines AI's search and optimization with human expertise. The AI provides explainable recommendations, and the human experts modify constraints and objectives based on strategic priorities. This figure illustrates the collaboration loop. AI proposes candidate layouts with rationale, and humans review, adjust constraints, and approve or revise decisions. Over time, the AI learns from these decisions, and stakeholders gain confidence because recommendations are explainable rather than opaque. Explainability is a key enabler for adoption. Feature importance can show which design factors drive performance. Sensitivity analysis can show how changes in constraints alter the recommended layout. Counterfactual explanations can show why an alternative was rejected. Together, these tools allow humans to understand trade-offs and make defensible decisions. At the Port of Hamburg's container terminal, Altinverter, the AI proposes a configuration with 18% higher theoretical throughput. Human experts recognize that narrow aisles create safety risk during high wind conditions. The refined design achieves a 14% improvement while maintaining safety. Reported outcomes include 92% stakeholder satisfaction, 67% faster decision-making, and 23% better long-term performance than purely AI-optimized solutions. These practice questions test whether you can translate the concepts into concrete models and algorithms. For Tier 1, you are asked to formulate an integer programming model with flows and transport costs, and then extend it to a 2-scenario stochastic setting. For Tier 2 and 3, you are asked to design and analyze heuristic and metaheuristic methods, including bounds, pruning, and decision tracing. Tier 5 and Tier 7 questions test whether you can evaluate economic impact and long-term value under realistic constraints. Terminal layout is a strategic decision with long-term consequences. Good layouts increase throughput, reduce congestion, and reduce equipment requirements. Stochastic programming provides a rigorous foundation under uncertainty, while branch and bound and harmony search provide practical optimization tools. Digital twins reveal second-order bottlenecks before construction. Human and AI partnership ensures solutions remain safe, practical, and aligned with real-world constraints.